Okay, so in this video, we're going to have another look at this question. And if you'll remember if you've seen the other video I did on this, you'll know that the mass of this object here is 1.2 kilograms. Okay, and therefore the weight is 1.2 times 9.81, which gives you 11.8 newtons. Okay, so we know that the weight of this object here is 11.8 newtons. And this situation here, we've got this object that's supported on its corner here and also supported by this tension in this string here. And the object's not moving, so everything is in equilibrium. Okay, so if we cut the string, the object would presumably fall this way, but the string is holding it stationary. All right, so we know this 11.8 newtons is acting downwards here. And we know that this tension here is 5.1 newtons. We were also told that in the question. So we know that T is 5.1 newtons, okay? So sometimes with these types of questions, you're asked to calculate what the upward force would be at the support. So this support is providing some kind of upward force here, and we don't know what that force is. It's a force F, okay? We're going to work that out. How are we going to do that? Well, we know the weight here is 11.8 newtons, okay? So we know that's acting downwards. And we know that there's another force acting upwards here. So this force acting upwards here, okay, is going to be a component of this tension, okay? So this force acting upwards here, acting vertically upwards, is a component of this tension because this tension splits into a vertical component and a horizontal component, okay? Now we know this angle here is 40. That horizontal component could be drawn up here, okay? We can say that from the parallelogram rule. So this 5.1 newtons can be split into a vertical and a horizontal component. They are at 90 degrees to one another. I can't quite fit the angle in there, but they're 90 degrees to one another. So this is a triangle, right angle triangle. This is the hypotenuse and this is the adjacent. So we know that cos of 40, because that's the angle there, is equal to adjacent over hypotenuse, and therefore cos of 40 is equal to adjacent over 5.1, and therefore the adjacent, because the hypotenuse is 5.1 newtons, so if we rearrange that, 5.1 cos 40 gives us our adjacent, which will come out as 5.1 cos 40, 3.9 newtons, okay, or 3.91 newtons. Okay, so 3.91 newtons. So we know that force there is 3.91. We know this force here is 11.8 newtons. So what's this force? Well, if this situation is static, if it's in equilibrium, then there must be no resultant force on it, okay? No resultant force. So the sum of the forces must equal 0. There's no resultant force acting on it. So if 11.8 newtons is acting downwards, there must be an equal and opposite force acting upwards. Okay, so that is to say that 11.8 is equal to 3.91 plus this force F here. The total upward force must be equal to the total downward force. So F is just going to be equal to 11.8 minus 3.9. Maybe I should have written this as 3.9 rather than 3.91, but it doesn't really matter. So 11.8 take away 3.91 is going to give you 7.89. In fact, I definitely should have written that as 3.9 because that was 2 sig fig. That's 2 sig fig, so that should be 2 sig fig. So let's get rid of the 1 there. So 11.8 take away 3.9. Sorry about that. Is going to give you an answer of 7.9. Okay, so we know that force there is 7.9 newtons. Now, can we check this to see if it is correct? Yes, we can. We can now say, well, we're going to take this as our pivot point. So that's our pivot point, and we're going to look at this in terms of moments. If the whole thing is in equilibrium, then we know, whoops, sorry, I've messed the camera up there. Let's reline that. We know that the sum of the clockwise moments must equal the sum of the anti-clockwise moments. Okay, Now, if this is our pivot point, okay, then we have two forces to consider. We've got this force here and this force here. Usefully, they're both perpendicular to the horizontal, okay? This force here is acting at a distance from here. We already worked out in a previous video that this distance D is 0.25 meters. So therefore this distance here is 0.5 meters. So this weight, if this is our pivot point, the weight is acting, is providing an anti-clockwise moment at 0.5 meters from the pivot point. That's the perpendicular distance of this weight from the pivot point. Clockwise, we've got this force providing a clockwise moment, and it is acting at 0.75 meters from the pivot point. So clockwise, we've got F times 0.75 is equal to 11.8 newtons, because that's the weight, multiplied by 0.5 meters. Okay, don't need the meters there. So if we rearrange that, we're going to then get F is equal to 11.8 times 0.5 divided by 0.75. I should include the significant figures here. So if you work that out, you're going to get 11.8 times 0.5 divided by 0.75. And that gives you 7.9 newtons. So that's just check. That's just a different way we've used the principle of moments, and we've used the fact that there's no resultant force on the object, two different methods to prove that this force F here is 7.9, and they agree. So therefore we can be really confident that our answer is right.